That's just fair. More money.
Okay, good morning, everyone. I want to welcome you to another statistical machine learning class. Of course, today and this week in general, we're going to be focusing on theory of convex functions. Why do we, uh, why are we interested in learning this? I need you to pay attention because we don't just do what we do. We got a reason why we do what we do. Before I'm going to continue, is everyone hearing me clearly, right? Including those of you at the back. Okay, thank you so much, and those on Zoom as well. Okay, so yeah, thank you for confirming that. Now, at times our ambition may be to optimize. Our ambition may be to seek minimum value of a function or maximum value of a function, or in general, we're seeking an optimization goal. And let me tell you this: what we want to do this week is the theory that will guide us to be able to achieve solvable or easy optimization, because without this, there's going to be an issue. We don't want a situation where we've committed resources to an exercise, and at the end of the day, the recommendation from that does not see the light of the day. We don't want to mislead. And that's why we need a theory of convex functions. I remember in the last class, I actually introduced convex to you, that our function need to be to have this kind of nature before we can achieve global minimum in a situation where we are actually minimizing a function. We don't want our algorithm to get stuck in a local territory. We want our algorithm, we want to have a way to translate a local minimum into global minimum when you are seeking minimization, or you want to have a way to translate local maximum into global maximum as well. And that's why we need to be guided. And that's why I want to walk you through the theory of convex functions. In the outline, I'm actually going to give you examples of convex functions within univariate and multivariate setting, because within univariate setting, where you're only focusing on one variable at a time, you may be looking for the value of such variable that will minimize your function. But what if in a situation where in a multivariate setting where you got a lot of variables, you may also want to minimize as well, where you are seeking the values of features that can minimize the function. Then I'm going to walk you through the conditions. Okay, convexity condition, the one I will call strict and the one that I will call strong. What makes strict convexity different from strong one, I'm going to walk you through that here. And I'm also going to talk about the first and second order characterization of convex function, because we have several ways of investigating convexity. Okay, and I'm also going to walk you through different differentiable classes that will enable us to distinguish between or that will enable us to investigate the convexity of a function. So I'm going to walk you through three differentiable classes as well. Then we're going to have work examples on convex functions. And this material that I think I have 50 pages. Okay, I'm going to go, that's what we're going to go over this week. Where you know, whichever page that we store, that's where we're going to continue from on Wednesday. Okay, so let's get started. And I need you to pay attention. Are you all ready? Okay, pay attention. Let's talk about convex optimization now. You know why we are here in the first place. We are here because we want to have some understanding, okay, of how our function should look like if we actually want to tell a success story. Success story of what? Success story of, you know, you achieving your optimization goal. I want you to pay attention to what I'm actually going to be showcasing. Let's start with this. Okay, I want to minimize a function. This is a univariate function. It's a univariate because I'm only having one variable at a time. My variable here is W. We are seeking to minimize this function as subject to W. And that we believe that W, that variable, is in a set C. Okay? You know, whenever you see an uppercase like that, okay, we refer to that as a set, like set of numbers. Okay? Numbers in the domain. Okay? Now, this is what happened. I want to minimize a function like this. This is a typical of what we did in statistics. For instance, I want to minimize, please pay attention. I actually want to minimize this guy. Can you see this? Okay, if you take a look at this guy, HW is a linear model. You want to use a linear model to fit a data Y. I'm using this linear model to fit a data Y. I'm using model to fit data. And I want to have a measure, okay, how my model fits my data. If I want to have that measure, I'm actually going to consider a distance. And the algebraic operation that's actually going to come in is minus. My model minus data is like I'm actually depicting reality with my model now. Now I want to see the distance. But what do you think would be my goal? My goal is to minimize the distance between the model and reality. And that's what I'm doing here. Okay? You know, I actually want to minimize that. Okay? If you take a look at this. Okay? That's a squared difference between the square absolute difference between the model, the linear model SW, and the data Y. Okay? And if you take a look at this function, before I will succeed in minimizing this, I have to investigate the convexity of this function. I'm going to say that again. Before this particular, before I will be able to achieve my goal of optimization, which is minimization here, what guarantee the global minimum here is when the function is convex. Then I now want to investigate the convexity of this particular function. Does that make sense? Now you understand what our intention is. We don't just do what we do. We got a reason why we do what we do. But you know what? If you take a look at this, we are taking, don't forget, the module that you are using. This is the module, right? That's the module you are using. The module is a function of W. Don't forget, what you are minimizing is f of W. Okay? And we want to believe that very W is taking data points in this set C. And it's of D dimension. And you know what can guarantee that? What can guarantee convexity? Number one, okay, that set C has to be convex first. Okay, that set C has to be convex. What do I mean by that? Please pay attention. If you don't understand, ask me a question. The very first condition is where I'm taking my data point from, the set that I'm taking my data point from has to be convex. What do I mean by convex? Okay, it means if I take any two data points from that set C, okay, and I try to now draw a straight line, okay. When I draw a straight line, just like what I showed you last week, when I draw a straight line, okay, that should stay in the function, not outside the function. That's what we mean by convex set. Any 2 points, choosing from the set, okay, by the time you connect, by the time you put it to a function and you connect it, it should stay inside the function, not outside. When it is inside, then you are working with a convex set. When it is outside, you are not working with a convex set. You have violated the condition number one. And that's not good. That is exactly what I mean here. Okay? And after you have investigated, we're now going to go into the next condition. The next condition, like I said, let me do this. The first condition is to ensure that we are having a convex set. And what convex set means, any 2 points that you choose from the set, okay, when you try to connect that, with a straight line, okay, it should stay in the function. It should stay inside the function. And when that happens, the next on the line is to now investigate the structure of your function. I want to go back now to the structure of my function. Oh my God. When you take a look at in the function, number one, I'm actually seeing a norm. This is what we call a norm. Can you see that? I'm seeing a norm. Okay. Oh, a norm is convex. I'm going to show you how every norm is convex. Okay. Now, when a norm is convex, the square of a norm is also convex. Now, this is what is happening here. I'm actually squaring a norm. A norm is a convex. The square of a norm is also a convex. Therefore, I think I've been able to satisfy the conditions. Okay? Now, another thing I should talk about is this. Because we could have a constraint optimization. We can also have unconstrained optimization. Do I actually want to restrict, okay, a particular value, the value of the variable? Okay. Now, when I say this, then it means I'm saying I'm restricting that to non-negative. I don't want negative. I'm talking about W right now. Okay. Constraints also matter if you want to achieve your goal of optimization. And you have to define that clearly. Okay? Now, I'm actually going to summarize what I've been saying. Take a look at that. I said, okay, we say that this is a convex optimization problem if, one, the set C is a convex set. the set of data point has to be convex. Not only that, the function, when I say function, the function you want to minimize have to be convex as well. Okay? Now, you now have that very story now. We now want to go into that theory of convexity. How can I show the world that the norm is convex? Because that's what I mean by norm. If you take a look at this guy, just this one, that's a norm. Okay? I have to show the world that norm is a convex. I also have to show the world that the square of a norm also a convex. Does that make sense? That's what I want to guide you through now. But you know what? I said something the other time about this guy, the first one. I said condition number one is that we should have a convex set. What do we mean by a convex set? Okay, now I'm going to show you using a picture, an image right now. Please pay attention. Take a look at this. And I want to define what a convex set means. Now, if I take any 2 points from a set, okay, and I draw a straight line, okay, and if that stay inside the set, inside the function, okay, if you stay inside the set, I'm actually going to say it's convex. Okay, we have verified this guy for this shape. When a set is of that shape, when you take any 2 points from that and you draw a straight line, it's going to stay inside. For this guy, it's going to stay inside. For this guy, it's not going to stay inside. Now, I'm just trying to show you the picture now, okay, of what the convex sets look like. Now, like I said again, you pick any 2 points inside the shape, inside each shape, pick any 2 points. When you pick the 2 points, draw a straight line between them. Okay? When you draw a straight line between them, you want to see whether it stays inside the set or not. When it stays inside the set, then it is convex. That means you have verified condition number one before you move to the other condition. Okay. I'm going to move right now. Moving to the next one. Take a look at this. Now we have other conditions, but I'm actually want to walk you through I want to use 3 differentiable classes. Okay, to investigate convexity. I'm going to say that again. I want to use 3 differentiable classes. When I say 3 differentiable classes, what do I mean? We could have a function, and that function is continuous and not differentiable. That's number 1 class, which is this guy. And that's why I call it C0. The 0 that you are seeing is, not necessarily differentiable, but it's continuous. I'm going to talk about C1. It is continuous and has and is first differentiable. I'm going to talk about this guy, C2. It's continuous and first derivative exists and second derivative exists. So what I want to do on this page, I actually want to walk you through how we can use 3 different differentiable classes to investigate convexity. Are you with me? Are you following me? Okay, if you are not getting this story, please let me know. Okay, now let's get started with that. Now, take a look at this guy. You know what C0 means? I said C0 means we have a continuous function, but not differentiable. Now, if to have a convexity, we don't have a strict requirement that the function should be differentiable. If the function is not differentiable, but it's continuous, okay, that can still be convex given certain condition. And that's what I want to talk about now. What is the condition? And I said it's convex if the area above the function is a convex set. The area above the function has to be a convex set, which means we have to investigate the area. Okay, we have to investigate the area above the function, not inside, not below, but above the function. Okay, that is how to investigate convexity for a continuous function that is not differentiable. Now, another way is this. Please pay attention. Okay, I said a function is convex if the function is always below its chord between point. Oh, always below. Oh, you remember the other time when I draw something like this, and I put the line, and this is the line. If it is below, the functions have to be below the line. That's why we say it's inside it. That's what we mean. Okay, it's below its chord between point. When I take any 2 points within the function, within the continuous function, okay, and I draw a straight line, it has to stay in the, or it has to be inside, below the chord. That's what we mean. Now, I think I just walk you through 2 different ways of investigating convexity for a continuous function that may not necessarily be differentiable. I want to go into another class now, another differentiable class. Now, the differentiable class that I want to talk about is what we call C1. When you see C1, like I said, we have a function that we are considering for optimization, and that very function is continuous and is also differentiable, but differentiable to order 1. First, differentiable. Okay? Now, if it is differentiable to order 1, how can we actually ascertain convexity? How can we ascertain convexity? Then we have to consider the targets. And that's why I said, please pay attention. I say, the function is always above the target planes. You're going to see that mathematically. How it has to be above, the function itself has to be above, that is greater than, okay, the target plane. That is for a function that is continuous and first differentiable. But how do we investigate another differentiable class? In this differentiable class, it is continuous, both first and second derivative exist. How can we investigate the convexity in this type of function? And I want you to listen. Now, to investigate convexity, we actually want to guarantee a curve everywhere. What do I mean by guarantee a curve everywhere? Oh my God. Mathematically, if I'm talking about univariate function, f of w, that prime, do you see? Do you all see this prime? That is first derivative, second derivative, okay? And it is greater or equal to 0. When it is greater or equal to 0, then that can guarantee a curve upward everywhere. I think our models don't fail us. Our algorithm don't fail us. At times when it's going to look as if our models are failing us. Our models are not failing us. Maybe we are the one that we're not doing the right thing. And, this is a way we're just walking you through how you shouldn't waste resources. We don't want it to mislead. We want it to be guided. Depending on the type of functions you have, you could have any kind of function. But whatever function you have, you need to first understand what is the nature of this function. Okay? Now, you can use any of these differentiable classes to investigate for convexity. Let's come here now. You know what? Do you know that I can give you some functions? Several functions. We have so many functions in the world. Okay? You can say quadratic function, linear, constant, exponential, negative logarithm, negative entropy, logistic laws. Okay? If I want to ask you to investigate convexity, I will tell you the approach that I want. What if I say, okay, investigate convexity using the second order condition? Second order condition. It means I actually want you to use the second differentiable class to investigate. And to use the second differentiable class to differentiate, you can see all of this. Each of this is a function of W. This is a univariate function. If I'm seeking minimization on on any of these functions, if I want to use the second order condition, I must be ready to perform a second derivative. The first derivative, the second derivative, and I compare whether the result that I have is greater or equal to 0. When it is greater or equal to 0, of course, then I'm actually going to say the condition of convexity met using the second order, using the second order condition. Is there any question? Now, you know what I'm actually going to test? I'm going to test your knowledge of calculus here, because there's no way you'll be able to investigate this without knowledge of calculus. So if I were you, what you need here, the prerequisite knowledge you need here, is your basic calculus. How do you differentiate a particular function? Not only first time, but second time. You need to revisit that. Okay, I'm moving. Do you now know what I want to do now? And I want to concentrate more on the first differentiable class. Don't forget, I told you we got 3 differentiable classes when it comes to investigating the convexity of a function. Now, I actually want to elaborate more on the first differentiable classes, which I call C0. Can you take a look at that? Whenever you see C0, that is the first differentiable classes. C0 means I have a continuous function, but not necessarily differentiable. So if it is not necessarily differentiable, I'm not using calculus for this class. I'm not interested in differentiating it. Now, how can we investigate convexity using this class? Let's get started. Now, take a look at this. Don't forget the other time, one of the ways to investigate convexity using this type of class that is not differentiable is to look at the area above. Okay? Now, I need you to pay attention. This is the kind of curve that we have. Okay? When you take a look at this kind of curve, you remember the other time I also mentioned this. Please pay attention. Take a look at this. I mentioned taking 2 points in a set and draw a set line. And before the function can be a convex, that should stay in the function. Okay, now we can investigate that now. Okay, now take a look at this. Okay, we choose 2 points. Oh, we choose W and V. 2 points in the set. Don't forget, in the convex set, and we draw a straight line. This is the straight line that you see, the dotted line here. And if we can show that stay in the function, If I want to show mathematically, please pay attention. If I want to go analytically now, this is what I'm actually going to show. Where is the chord? This guy here. This guy here. Okay, give me 1 second. Let me clean that. This guy here is the chord. Is this particular straight line. Now, this guy here is the function itself. Oh my God. What is that sign? Take a look at the inequality sign. Then it means the function stay inside the straight line. It stay inside the chord. That's what I mean. That's why you have that inequality. Don't forget, some of you may be wondering, what is the meaning of this theta? What is this theta here? What is it doing? That is the weight. That is the weight, because I'm actually choosing point between W and V. Okay? Between W and V. Okay? That's why it's this weighted. Okay? That's what it means. And you know what? A situation where the function stay in the chord, below the chord. And that is why you have this guy here, less or equal. But you know what? If that inequality sign change to greater than sign, you are no longer talking about convex, but you are talking about concave. Have you heard about concave? There is convex, there is concave. Let me write it. Concave. That would be concave. When it doesn't stay inside. I'm still going to have the whole equation. Except that the inequality sign is going to change from less or equal to a greater than sign. Does that make sense? Okay. Now, that's exactly what I mean. And let me tell you this. Because right here we're not actually focusing on anything differentiable. Okay. We believe the change is 0. Okay. And if that happens, then we're actually going to say W is the global minimum. Global minimum, which means when we are minimizing the function, we've been able to get the most minimum. We don't want to get a minimum in a particular local, in a local neighborhood of the domain. We want to get the minimum across the domain. That's our intention. Okay. Now, I need you to pay attention now. Do you know what I want to do next? I now want to investigate using this. I want to investigate using this to see whether if I have a function that is a norm, a function that is a norm, can we investigate it for convexity? I remember the other time I was talking about least squared, where we have a square of the norm. And I said, a norm is convex. The square of a norm is convex. But the question is, how do I know a norm is convex in the first place? I want to investigate now. Please pay attention. Pay attention. I want to investigate the convexity of a norm using the first differentiable class. The first differentiable class is C0. Don't forget that. Now, this is my function now. That's a norm. Whenever you see that, that's a norm. That is not an absolute value. An absolute value is just going to be just a single, just going to be that. But when you have this one and you have that one, you're talking about norm. If I'm seeking a minimization for a particular function that is a norm, how can I guarantee convexity? I'm going to investigate that. Okay, please pay attention. Using this guy here. Using this. Because this is a condition for convexity. That's what I'm going to use. Now, in using that, I need you to pay attention. How can I rewrite this to look like this? Is this. Can you see that? I have a norm of W, right? When I have a norm of W, I'm actually going to assume that I have a 2-point W and V, and they are weighted. Weighted, that's why you have a theta and 1 minus theta. Then I have to write that. So now you can see this guy now is extended to this guy. Can you see that? Now I'm having a norm. Now, what I'm now going to do right now, okay, what I'm going to do right now is actually to use what I call the triangular inequality law. Okay, I remember when the absolute value of A plus B, or the norm of A plus B, is going to be, norm of A plus norm of B, or stuff like that. So let me tell you this. When I have this guy, from mathematical law, it is less or equal to this guy from mathematical law. And that's why I believe you've taken some mathematical classes before, or you get qualified to take this course. You need to revisit that. Now, by absolute homogeneity, I can have that guy to look like this. From there, I have this one. And finally, I can say this is that. Now, if I have that, then I can actually guarantee, because f is below, I can guarantee that the f, the function, is always going to be below the chord. And when it is below the chord, then it's convex. When it's below the chord, it's actually convex. Now, let me tell you this. We have mathematically proved and statistically observed that all of these are convex. Okay? Can you see that? The first one, absolute. You may be working with your absolute function. Okay? So that is convex. You may be working with a norm of W. You may be working with absolute norm, square norm, and so on like that. Okay? In lasso regression and ridge regression, we use norm, L norm, as a regularization. Okay? So, we will be able to achieve that because the norm that we are using is actually convex. Be able to achieve our minimization goal, okay? And we know the reason why we're bringing the regularization in, okay, in case of overfitting. We actually want to control overparameterization that will lead into overfitting in a situation where you have high-dimensional data, okay? So we're still going to talk about all of that, but the major story now is that all of these have been confirmed to be convex. You are free to use them in minimization, and using them, you'll be able to achieve your goal. Okay. There are some operations that we did, okay, that may eliminate convexity. We want to guide you against operation that you do, okay, that will preserve convexity, so that we can actually, give you information that, okay, you need to guide against those ones that may eliminate convexity. And I need you to pay attention. Do you know at times you could have a complicated function, right? You could have a complicated function where you are adding functions, you are subtracting functions, you are dividing functions, you are doing composition of functions and so on like that. If a particular function is convex, let's say you are working with two different kind of functions, okay, and each of them is a convex. There are some mathematical operation that does not preserve convexity. And there are some that preserve convexity. We just want to let you know. Let's take a look at the one that preserves convexity. Take a look at this. If I have two different functions, f and g, okay, and I do non-negative scaling, you know what we mean by non-negative scaling? Maybe I have f of w is already a convex. I multiply it by 5. or I multiply it by 10, or I multiply it by 50, or I multiply it by half, or I multiply it by a non-negative value, that is still going to be convex. But when you multiply by negative, you have truncated, you have eliminated convexity. That's all we wanted you to know here. Let's go to number 2. Another operation. Oh my God. Let's say you have a complicated function h of w, and you arrive at the complicated functions by addition of 2 different functions. Let me tell you this. Your lasso regression, your ridge regression is like this, where the first function has to do with a least square distance, the sum of a least square distance, and the second one has to do with the norm, the regularization. When you are adding 2 functions that are convex, the addition, the sum is still going to be convex. This has been verified. Now, what if in a situation where you have 2 different functions, each of them convex, and you're only interested in the maximum of the 2. When I say maximum of the 2, I quickly want to take you back to high school. I remember in high school when you were working on a calculus that we call area under a curve. I remember you normally talk about distance between 2 curves. Somebody remember that? Okay, AP calculus. Okay, difference between 2 curves. Okay, area, I'm trying to look at the area. Now what I'm going to do, I need to identify which function is at the top, which one is at the bottom. Then I will subtract, then I will perform integral. Okay, now here, if I have 2 functions, and within the domain, I identify the maximum of the 2 functions is always going to be convex. But you know what? The minimum of the 2 functions is not convex, even if the 2 functions are convex. Now, in your high school, you talk about composition of a function. The composition of a function is you put a function inside another function. Oh, f of s is convex, g of s is convex, and I'll put g of s inside f of s. Is my composition convex? Okay? It is not all composition that are convex. But if your composition is linear, then it is convex. Take a look at it. If I have h of w, I have h of w, okay? And now consider AW, which is a linear combination, then it's still going to be convex. Now, these are operations that actually preserve convexity. Okay, now, away from that, we now want to consider example. Has anybody heard about support vector machine? That's what we call SVM. Support vector machine is very useful in a classification problem where you actually want to identify boundary. Okay? Now, if you want to identify boundary, because you actually want to classify correctly, maybe you're working, maybe customers approach a bank to get a loan, and the bank official want to classify the customer. They want to investigate whether, they want to determine whether it's going to default or not. They can use support vector machine. They can use logistic regression. They can use random forest and so on for the classification. But you know what? If we're using support vector machine, okay, this is the objective function that we normally want to minimize. But you know what? I want us to investigate this objective function for convexity. Let's start by investigating each component for convexity. I needed to pay attention. I'm going to start from, okay, I'm going to start from that. Oh, norm. Oh, norm is convex. We're okay with that. Oh, the square of norm is also convex. The square of norm is convex. Take a look at this. Oh, provided my lambda is positive, lambda over 2 multiplied by that is also convex. That is what we call non-negative scaling. You remember I talked about non-negative scaling, which is this guy here. Multiplying non-negative by a function. If that function is convex, that is still going to be convex. What do we just find out now? What do we just investigate? We now realize this particular component is convex. If that guy is convex, let's go to the another component. Please pay attention. I want to investigate. One second. I want to investigate this guy now. If you take a look at what I have inside, the guy is convex. And if I want to go by this guy, if I want to go by the maximum of that, we're told that also preserves convexity, then I'm actually going to say the whole of this guy is convex. Now, if this guy is convex, this guy is also convex, okay? What about adding them up? What about adding them up? Is he also convex? I'm actually, oh my God, I'm going to use this particular rule here that said if each function is convex, adding them up is also going to be convex. And do you know the implication here? I'm going to tell you what the implication here means. Implication here is, even though this particular function is complicated, but this function has already passed a test of convexity, and what is the consequence of this? Passing a test of convexity means we actually going to, this can guarantee global minimum. Does that make sense? That is the investigation. Okay. You know, I've just investigated. We've been talking about the first differentiable class. Okay, I'm actually going to stop here today. I'm going to explain this before I go. Now, this is the second differentiable class. In the second differentiable class, the function is continuous, and at the same time, the derivative to the first order exists. And what is the condition for convexity? The condition is that the function should lie above the target. Okay, now, you know what we're going to do? Let's write it. Look at that. Which equation represents the target that we just talked about? This is the equation that represents the target. Okay, you can say the equation that represents the target is actually having differential. Can you see that? That's a gradient. That's a derivative sign. Okay, now which of the function is representing the original function is this guy. Okay, now the rule is that if I want to go by first differentiable class, the original function has to be greater, has to be above the target planes. Now, this is writing it equation-wise. If I actually want to show you the image, this is the image. Oh my God, the straight line here. Can you see the straight line? That straight line is actually the tangent, and the curve. Look at the curve. The curve is above that straight line, and which is what we're talking about here. And don't forget, the set has to be convex as well. Now, in that situation, the moment the derivative equal to 0, that this is guaranteed. It is guaranteed that the original function of W will actually be above the target plane. And when it's above the target plane, the W that you obtain, the minimum value of W that the minimum value of a function that you obtain is actually going to be a global minimizer. I will start from the second differentiable class on Wednesday. But you know what? The Wednesday class is actually going to be on Zoom. We are not meeting in person on Wednesday. Please check the announcement section. I just put that. The next time we're going to meet in person will be on Friday. For Wednesday, you log on to the Zoom link. Okay, that's all I got. Be sure you all stay safe. Have a lovely day. Bye for now, everyone. Rest of you online, is there any question? Are you good, right? Okay. How are you? I'm good.
I have to say, even though it looks I took calc